We know that file is the logical unit of storage and it is an abstract data type. So for an abstract data type, we also need to consider the operations that can be performed on them. Now the operating system can provide the basic system calls to create, write, read, reposition, delete and truncate files. Apart from these basic system calls, there can be other system calls also. So let's take a look at all these operations. First is creating a file. So there are two steps which are necessary to create a file. First, we have to find some space within the file system so that the file can be placed over there. So whatever file is created, it needs a space in the file system. The second step is that an entry for the new file must be made in the directory. We know that the directory is keeping track or keeping information of all the files. So for the new file that is created, an entry for the new file must be made in the directory. After the file has been created, we can perform other operations on it, like opening the file. So all operations, if it is a read operation, write operation, reposition operation, for these kinds of operations, we will first require to open the file. The create and the delete, these are the only two operations which do not require the file to be opened. So all operations apart from these two operations will require the file to be opened first. If this system call, which is opening the file, if it is successful, this call will return a file handle. This file handle is a numeric integer or the file identifier, and this can be used as an argument in other calls for file operations. If we want to write into the file, the system call will specify the open file handle and information to be written into the file. So the file handle will have to be given into this system call for writing the file, and using this identifier, the opened file can be written into. So the system will use the write pointer to the location in the file where the next file is to take place. So every file will have some pointer. So suppose if this is the pointer where the file has to be written into, the system will keep track of that and it will point to where the next write is to take place, and the write pointer will be updated whenever the write occurs. So if few bytes or whatever data has been written into, this file pointer will now be updated to point to the next write. Reading the file system call specifies the file handle again and where in memory the next block of the file is to be put. If the file is being read, suppose it is there on the disk over here, and if it is being read, that means that particular block will be picked up from the disk and taken into some memory block. So where exactly in the memory this new block has to be taken, that information also has to be given. So the system will keep a read pointer to the location in file where the next read is to take place. So one pointer is needed to specify where exactly we want to read from, and the next information is about where in the memory this block has to be placed. Once the read has taken place, again the read pointer is updated. So a process is usually either reading or writing into a file, and the current operation location, that means the read pointer or the write pointer, it can be kept as a per process current file position pointer. So rather than keeping two separate pointers, one for reading and one for writing, one common pointer can be kept, and this can be the per process current file position pointer. So if a particular process is using that file, then where exactly that current file position is for that particular process. Multiple processes could have opened the file and each process might have its own current file position pointer. So this information is kept as a per position current file position pointer. So now both the read and the write operations can use the same pointer. So this reduces the space as well as reduces the system complexity of maintaining two pointers. Repositioning within the file is another file operation. That means the current file position pointer of the open file is repositioned to a given value, and this is also referred to a file seek. So currently whatever is the position of the file pointer, it can be repositioned to a new value. If we want to delete the file, then the directory has to be searched for the named file, and from the associated directory entry, all file space has to be released so that this space can be now reused by other files that are being created or modified. Now the directory entry also is erased or marked as free. So the information of this file is now deleted from the directory as well. If the file has to be truncated, that means the user may want to erase the contents of the file but may still want to keep the attributes. So this allows the attributes to remain unchanged except that the file length now becomes 0, because now if you have erased the contents, the file length is no longer a positive value. The file length can be reset to 0 and its file space can be released till the time it is remodified and more data is added. Now most file operations we have seen, they will involve searching of the directory for the entry of the named file. And to avoid the constant searching, many systems require an open system call before a file is first used. Like if it's a read operation or a write operation or repositioning operation, that means the file has to be first open. So some systems will implicitly open the file when the first reference is made, so that there are not repeated searches in the directory for multiple system calls. So if it is a read system call, then that file will automatically be opened. Create, delete, these system calls work with closed rather than open files. So some system calls like create and delete, they will work with closed files and they do not require the files to be opened. Let's take a look at the open system call. Now the open system call takes a file name and it will search the directory for that particular file. It will copy the directory entry into the open file table. So an open file table is maintained and the directory entry will be copied into that open file table. Now this system call will return a pointer to the entry in the system-wide table. So the system is maintaining a system-wide table of all open files, and the entry of the directory for that particular file will be kept in the system-wide table and a pointer will be returned. Now this pointer will be used as the file handler for other operations. So it will be used in all input-output operations and it will avoid searching the directory again. This can also accept access mode information. Now this file handler will also be used to check the access mode. So if any user wants to write into that file, it will be first checked whether that file allows those write permissions to the user or not. So the mode is checked against file permission. If request mode is allowed, then the file is opened for that process, otherwise not. Now there is a possibility that several processes may open the file simultaneously, and this may occur in a system where several different applications open the same file at the same time. So how is information about this kept? So the operating system uses two levels of internal tables. One is the system-wide table that we just saw, and another is a per process table. So in per process table, all the files that have been opened by that process will be maintained, and in the system-wide table, all processes which have opened any particular file, so information of all files opened by any process, that will be maintained. Now let's take a look at the per process and system-wide tables. In a per process table, that means for each process a table is being maintained. This will track all files that the process has opened, and it will store information regarding the use of the file by that process. That means what is the current file pointer for each file for that process only, access rights to the file, accounting information. So now if suppose let's say P1 has opened a particular file F1 and P2 process P2 has also opened file F1, then for process P1 there will be a process table, and for P2 also there will be a process table, and F1 will have an entry into both, and whatever is the current file pointer for P1, that will be kept in the process table of P1, and whatever is the current file pointer for P2 for file F1, that will be kept in the process table for P2. And each entry in the table will point to the system-wide open file table. Now the operating system is maintaining the system-wide table, so F1 entry would also be here, and each entry over here, whatever is the information, is being maintained by the system-wide table over here for this particular process. So in the system-wide table, whenever a file operation is requested, the file specified will enter via an index into this table. So no searching is required. And when the file is no longer being used, it is closed by the process or program that opened the file terminate. So if P1 is not using file F1, it is closed by it when this program P1 terminates. So if P1 terminates, then this entry will also terminate, and the entry for P1 in this system-wide table will be removed. So the OS will remove its entry from the table. So suppose F1 currently in the system-wide table it specifies that P1 is using it and P2 is using it. So when P1 terminates, its entry from the system-wide table will be removed. Now the system-wide table, it contains the process independent information. So now this is only keeping information of which all process has opened the file, but apart from that it keeps information about the location of file on the disk, access dates and file size. So if this is the system-wide table and let's say F1 and F3, so whatever processes have opened it, let's say this F1 has been opened by P1 and P2, F3 has been opened by P4. Apart from that, what all information is here is the location of file on the disk, the access date and the file size. So if any process P1 which is using file F1 in the per process table, the location will be accessed from the system-wide table. So whenever P1 wants to access F1, this file handler, the pointer over here, will point to this entry in the system-wide table, and the location of the file on the disk will be accessed from here. Once the file is opened by one process, the table includes the entry for the file. So if P1 has opened file F1, its entry has come over here. When another process executes an open call, so like if P2 also wants to access or open this file, then its entry also comes over here. So this new entry will be added to the process's open file table and pointing to the appropriate entry in the system-wide table. So this entry will also point to the entry in the system-wide table. Now this open file table also has an open count associated with each file, and this indicates how many processes have the file open. Like for F1, the open file count is 2 because 2 processes have already opened this file. For F3, the open file count is 1. So whenever there is a close, so if P1 wants to close this file, that means P1 is no longer using F1, so its entry from the system-wide table will be removed, and now the open file count will be decreased by 1. So whenever the open count reaches 0, that means the file is no longer in use by any process, so now its entry will be removed from the system-wide table. Suppose now P2 also does not want to use F1 and it closes F1. So this entry will also be removed from the system-wide table. Now the open file count has come to 0. Now this entry of file 1 will be removed from the system-wide table. So what all is the file information that is stored in the system-wide table? One is the file pointer. So if the file offset is not included as part of the read or the write system call, the system tracks the last read or the write location as the current file position pointer. So this is the file information that is being stored. Apart from that, the file open count is maintained, which tracks the number of opens or closes of that file, and on the last close of that file, that open file count will reach 0. As the files are closed, the OS can reuse the open file table entries. So the system will wait for the last file to close before removing the open file table entry, and when this file has closed or is not being used by any process, it will remove the entry of that file. The location of the file, this information also is needed to locate the file which is kept in the memory. Now this location of the file will be kept in the memory, and that means it is being taken from the hard disk and kept in the memory so that it can be accessed whenever required. So that means the system does not have to read it from the directory structure for each operation. The location of the file is available in the directory structure but is now kept in the memory for each operation, so that the disk need not be accessed again and again whenever an operation is required for the file. The access rights, this is required for each process which opens file in an access mode. This information is stored on the per process table so that the OS can allow or deny subsequent IO requests. So whether a user is allowed to access the file in which mode. So this information is kept in the per process table so that the user requests can be allowed or denied accordingly. Now some operating systems, they provide a facility for locking an open file or locking particular sections of the file. It is very similar to the locks that are used in the critical sections of the data. Now this file lock, it will allow one process to lock the file so that the other processes now cannot access it. This is useful for files which are shared by several processes. So if it's a shared lock, then several processes can acquire the lock concurrently, and this is usually in the read mode. Exclusive lock, that means only one process at a time can acquire the lock, and this will be used mostly in the write operations. So what are the file access methods? We know that file is made up of fixed length logical records. So this information needs to be accessed and read into the system memory. So there are two ways of file access, either sequential access or direct access. In sequential access, the information in the file is processed in order. That means one record after the other. So if this is the beginning of the file and this is the end, that means one record after the other, it can only go sequentially. The pointer can only move sequentially. So one record after the other is read. This is the kind of access that is used in editors and compilers. So if there is a call like read next, next is pointing to the next part of the file, that means the next block, and it will advance the file pointer which tracks the location to the next block. Similarly, write next is appending to the end of file. So if the current position is here, then the write will start from here and write a block over here, and the pointer will now access or change or update to the next write wherever it ends. Similarly, the read pointer will also update accordingly. Now files can be reset to beginning. So this pointer can be changed or updated to point to the beginning of the file. And on some systems it may be allowed to skip forward or backward n records. This kind of sequential access works well on sequential access devices and random access ones as well. The other kind of file access is the direct access, and it is also known as the relative access. Now here the read and the write, it does not depend, it has no particular order. That means there is no sequence to it. It allows the programs to read or write records in no particular order. Now the file is viewed as a numbered sequence of blocks or records. So suppose if this is the logical view of the file. So if this is block 0, 1, 2, 3, 4, 5. So if direct access, you can access any record directly. So we may read block 17, then we may read block 63, then we can write to block 11. So there is no particular order or sequence. Compare this to the sequential access, where you had to go only in a particular order. So here in direct access, there is no restriction on the order of reading or writing. This kind of access is useful when we have to access large amounts of information, like for example in databases. So whenever there is a query concerning a particular subject, then the block which contains the answer, it can be computed, and that block can be read directly to provide the information. Here in direct access, the access is through the use of this block number n. So read n would go directly to block number n, and information from that block will be read. Write n would be to write into this particular block, and no sequential or particular order is required. Now this block number is a relative block number, and this is indexed relative to the beginning of file. So the first relative block of the file is 0, next is 1, then 2, and then so on. Now this is dependent upon file systems or operating systems. In some OS, the relative first block might be starting from number 1. So these are the logical block numbers, but not the physical block numbers. The absolute disk address may be 13403 for the first block and 3452 for the second block. So 0, 1, 2 are the logical block numbers like this. This may be in 13403 block of the disk, this may be on 3452 block of the disk, and so on. So this allows the OS to decide where the file should be placed, which is the allocation problem, and helps prevent the user from accessing portions of file system that are not part of their file. So the operating system keeps information about all of this, and the user is not allowed to access these portions of the file system. We will look into the disk structure in our next video.